So one of the things that we do really well is, as far as touch goes, is perceiving details. Humans actually have a remarkable ability to perceive details, for example, on our fingertips. And there's different ways to measure this ability. One of the ways to measure this ability is to use what's called the 2-point threshold. And essentially what it is, it's this, let me see if I can come up with a quick example here real quick. So if I were to, now, I don't know if you can see this, but this is two little points on a pair of tweezers, right? So the 2-point threshold is basically how far apart, what's the minimum separation that I need to be able to perceive these 2 points as 2 separate points instead of just one. So obviously I'm going to perceive them as 1 point there, and then they're going to be 1 point there, but at some point I'm going to be able to feel that there's 2 points there. So that's the 2-point threshold. Now obviously the 2-point threshold is going to be much lower on your fingertip than it will be on the back of your head, right? So if I were to do this, right, and put it right about there, I could tell when I do this on my fingertip that that's 2 points. But if I do it on the back of that same distance on the back of my head, it feels like just 1 point hitting me in the back of the head, right? The grating acuity is where you put a grooved stimulus on the skin and ask the subject to indicate the orientation of the grating. So, you have these very fine lines on a surface, and you ask the subject, are they going across, are they going diagonal, or are they going up and down? And you start by putting the lines very close together, and then you separate them until finally the subject can tell, oh yeah, they're going across, or they're going horizontal or diagonal or vertical. And then finally, the raised pattern identification. Being able to identify patterns that are raised on a surface to determine the smallest size that can be identified. So if I have a raised pattern of, say, a circle on a paper, I can obviously tell a circle that big, but what if the circle was the size of like a period, right, on a printed page? Could I tell that was a circle versus a square, right? So how big, the dependent variable would be how big that circle or square object is, and I'm measuring how big it is, how many millimeters it is, before I'm able to tell whether it's, let's say, a circle or a square. Obviously, this is a skill that blind folks have. If you're blind and and you've been taught how to read Braille, obviously this raised pattern identification is a very useful skill, very used skill to have for people who are blind, who cannot see letters, and therefore they read by running their fingers across and identifying the patterns of dots that they encounter as they run their fingers across these lines of printed dots. So here's an example right here. Here's the Braille alphabet. And if you've ever tried, if you're a sighted person, and if you've ever tried to rub your fingers on some Braille, you'll probably notice you have a hard time doing it. That's because you haven't been trained. But you can be trained and taught how to read Braille. As you encounter each one of these patterns, you can tell, for example, if we go from A to B, you can tell that A is a dot in this position here, and then B is 2 dots, and then C is 2 dots as well, but the dots go in the other direction, and then et cetera, et cetera. And slowly but surely you can be taught how to distinguish these dots because our fingertips are very sensitive. Here is the 2-point test right here. So we just like I showed you, you can poke somebody with these 2 points, and you ask them, are the points, is it 1 point or 2? And then you keep increasing the distance, and the dependent variable is the distance between the 2 points. At which point the subject reports that they can detect 2 points instead of just 1. And then the grating, we have this little bar here that has these little indentations in it, and basically what you do is you press that down and you ask the subject, can you tell if the bars are horizontal or vertical? They report that to you. Since our fingertips are so sensitive to touch, there's a very high density of Merkel receptors in the fingertips. So then they're very tightly packed. Just like the cones are in our foveas for vision, the Merkel receptors are very tightly packed in our fingertips. And you can do 2-point thresholds and grating tests on the fingertips and show very fine levels of detail. So the 2-point thresholds will be very low in the fingertips, and you can easily tell what direction the grates are running when you do the grating test. Here's some data that shows what happens when the different bars are applied on the grating test for a Merkel cell versus a pacinian corpuscle. Notice here, and the comparison here basically is that notice that the Merkel cell, which the firing pattern is shown here on the left, notice that it has a very distinctive pattern of firing that corresponds to the width of the bar. So whenever, for example, whenever the bars are, say, so the bars here, these little bars are 0.5 millimeter. So you'll notice that the cell begins to fire when they're about 1 millimeter apart, even a little bit less than that. And as they get further and further apart, you'll see that the Merkel receptor fires stronger and stronger. So you see this very nice pattern here of firing whenever the Merkel receptors are detecting this grate. But the pacinian corpuscle, if you remember, the pacinian corpuscle detects vibrations. It is not sensitive to touch. It's sensitive to vibration. And you'll notice no matter how wide the bars are spaced apart, when you're feeling that little bar pressing on your finger, no matter how widely they're spaced apart, basically this thing just fires. It says there's something there, but I don't know how far apart they are, as opposed to here where it's firing stronger and stronger and stronger the further apart the bars are. This is a graph that shows us the relationship between tactile acuity, in other words, how sensitive you are to touch, versus how spaced apart the Merkel receptors are. And you see there's almost a perfect linear relationship between how packed in the Merkel receptors are. So here on the x-axis we have millimeters, the average spacing between receptors. So a low value means the receptors are very packed in tightly, and a high value here means the receptors are further apart. And then on the y-axis we have tactile acuity in millimeters. So the lower the number here, the more sensitive you are to touch. So you see the fingertips here, very sensitive to touch and very high density of receptors. And then the palm of your hand is not so sensitive to touch, much less sensitive than the fingertips, and also there's much less Merkel receptors packed in the palm of your hand. So there's mechanisms in our cortex, as I mentioned earlier, to help us with tactile acuity. The body areas that are most sensitive, that have the highest acuity, namely the fingertips, the lips, the tongue, and the genitals, have larger areas of cortical tissue that are devoted to them. This is very similar to the magnification factor that you see in the visual cortex for the cones and the fovea. The visual cortex, or the part of the visual cortex that receives information from the cones in the fovea of the retina. Now remember, the fovea is the spot of the retina that is the most sensitive. That part of the visual cortex is the most densely packed, the largest, that does most of the processing. And the areas with higher acuity also has smaller receptive fields on the skin. So Higher acuity also means that there are smaller areas of analysis or areas that are sensitive on the fingertips than there are, say, on the elbow. You have much larger receptive fields on your elbow than you do on your fingertips, because you need those very densely packed receptive fields to be able to detect very small changes in touch. So here's a map of thresholds of pain thresholds or touch thresholds, I should say. So the higher the bar, the higher the threshold, meaning that the less sensitive the part of the body is, and the lower the bar, the more sensitive the body is. So if we start with the toes and the soles of your feet, the soles of your feet and your toes are they're fairly sensitive. I mean, they're not that insensitive. But of course they have to be sensitive, right? Because you want to make sure you're not stepping on something that's dangerous, right? So they're kind of sensitive. The calf is very not sensitive. So you can get a big old nasty cut on your calf and it won't hurt that bad. Same with your thigh. It's not that sensitive. The belly, it's not that sensitive. The back, not that sensitive. The breast area, not that sensitive. But once we start getting to the upper lip, the nose, and the cheek, those are very sensitive areas. And of course they have to be, because the nose and the mouth are areas that allow external stuff to enter our body. So we get air and food and water entering our body through this part of our face. So it has to be very sensitive to be able to tell what's going in. The forehead's not that sensitive. Shoulder, upper arm, and forearm not that sensitive. Palm is starting to get pretty sensitive, and then of course we get to the fingers, which are our most sensitive parts of our body. This is a picture of the different receptive fields that we have represented on our body, and this is from I believe from rhesus monkeys. The mapping of the receptive field relative to the cortical area. Notice in the fingers, the receptive fields are very small. Each one of these little receptive fields corresponds to a spot on the cortex. And then notice as we go to the palm and then to the forearm, the receptive fields get larger because they don't have to be that sensitive. So the body doesn't devote as much coverage, as much resources to cover those areas here, because it doesn't have to be that sensitive. But the body does devote a lot of resources, a lot of different receptive fields to these areas because they have to be very sensitive. And notice here the 2-point activity on the finger. The same 2 points can are represented differently in the cortex. So the two, the measuring the 2-point activity, or the ability to detect 2 points. Notice it gets represented very well here as 2 separate points, but on the arm, you really can't tell if it's 2 points or 1 point.